and the difference in phase between two waves, and how to determine if there is constructive or destructive interference at a point in space where two waves coming from different sources arrive. So let's start by talking about the function sine of phi. That function is important because a traveling wave, right, is the equation that tells us the displacement of a traveling wave is a sine of kx minus omega t, like we talked in other videos. So the argument of the sine function, which is kx minus omega t, is what is called the phase of the wave. So the phase of the wave. So in terms of the phase of the wave, the displacement is a function sine of the phase. So if you have a snapshot, if you're looking at a representation of a wave in terms of the phase, you can tell that at different points on the wave you have different phases. So for example, at a point where the displacement function of the traveling wave has a maximum, a peak, the phase of the function there is pi over 2. At a point where the function has a zero, right here, the phase of the wave is pi. At the point where we have a trough of the wave, we can say that the phase of the wave there is 3 pi over 2. Another 0, 2 pi, next peak 5 pi over 2, next 0, 3 pi, etc., etc. So if you know the phase of the wave at a particular point, you know what the wave is doing at that moment, at that location in space. We know what's going to be the displacement of the wave if we know the phase of the wave at that position at a particular time. Now, the concept that's very important when dealing with the interference is the difference in phase. So if you have 2 points in space, for example, you could say that the 2 points in space have a difference in phase, delta phi, which will be given by the phase of one point minus the phase at the other point. So the point to the right has a phase of 5 pi over 2. The point on the left is pi over 2. So the difference in phase between those two peaks that you see there, that we've selected here, the difference in phase between those two peaks, consecutive peaks of that wave, is going to be 2 pi. So this is always the case. No matter what two peaks you're talking about, the difference in phase between two peaks is always going to be 2 pi. Of course, the difference in phase between those two peaks that have one peak in between will be, of course, from one peak to another, 2 pi, and from that middle one to the one on the right, there's another difference in phase of 2 pi, so a total difference in phase between this point and that point of 4 pi. So knowing the distance between 2 points, we can tell what's going to be the difference in phase. We have to count how many peaks are there in between, and that gives us an idea of what's the difference in phase between 2 points. Now, if we have a wave coming from a source S1, and we are measuring, we're located at that red cross point in space, knowing the phase of the wave at that point, the phase of wave number 1 at that point, is important because, as we said before, when there is a second wave arriving at that point coming from a different source, the difference in phase between the two of them is going to be important. So how would you determine what's the phase of wave number 1 at that red cross? So the difference in phase between two peaks is 2 pi. So to another peak that will be 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, and we have to add the pi over 2, which is the difference in phase between the beginning of the wave, which looks like it's starting at 0, and the first peak, which is the difference in phase of pi over 2. So the phase of the wave at the red x, it's going to be 12 pi plus pi over 2. Now, if there was another source emitting waves, and those waves arrive at the red x, then to know whether those two waves are constructively interfering or destructively interfering, we'll have to determine what's this phase of wave number 2 when it arrives at the red x. So we can count the peaks. That gives us a difference in phase of 2 pi. So 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, the beginning has a pi over 2. From the beginning point to the first red line that I drew there, there's a pi over 2. 10 pi is that intermediate difference in phase, and the final piece of the wave adds a difference in phase of pi. From a peak to a trough, there's a difference in phase of pi. Right? The other half of the wave is another pi to give you a total difference in phase between two peaks of 2 pi. But as you can see here, there is one peak here, then we are at the trough. The x is located in a point in space where wave number 2 arrives with a trough. So that's why we have this pi at the end. So what's the difference in phase? What's the phase of the wave at point 2? That would be 10 pi plus 1 pi, that's 11, plus pi over 2. And now we can calculate the difference in phase between the two waves. So one wave arrives with a phase of 12 pi plus pi over 2. The other wave arrives with a phase of 11 pi plus pi over 2. So when you subtract the two, you get that the difference in phase between the wave coming from source 1 and the wave coming from source 2, the difference in phase is pi. The difference in phase of pi, as we talked before, is gives us a destructive interference. Those two waves are going to interfere destructively at the point marked with a red X. As you can see in the picture, one wave arrives with a peak, the wave is up, and the other wave arrives with a trough. And when a peak is superimposed to a trough, the two would cancel out. The two waves are going to cancel out at that point. That is the signature for destructive interference. The difference in phase is an odd multiple of pi. Now, when we look at the waves arriving at a common point, coming from different sources, we just said that knowing the phase of one wave and knowing the phase of the other one is important because the difference in phases between them will determine whether the interference is constructive or destructive. Pi 1 minus pi 2 will tell us whether it's constructive or destructive. We know that the even multiples of pi, 0 included, give us constructive interference, and that the odd multiples of pi, 3 pi, 5 pi, 7 pi, etc., gives us destructive interference. Now, the usual way in which waves are represented in 2 dimensions is that people draw circles representing the location of the peaks of the wave. So, a wave that is emitted at that point at S1, so this is S1 right here. In the middle of that circle we have a source of wave, S1. So that source of waves is emitting a wave. The way we pictured before was the sinusoidal picture that represents a traveling wave, but a more common representation in 2 dimensions is to just represent the location of the peaks of the wave. So we see that a wave emitted at S1 that arrives at the red X would have a phase when it arrives at the red X, would have a phase that is equal to, this is 2 pi, from the center to the first peak, that's a 2 pi. Then another 2 pi there, so that's 4 pi, 6 pi, 8 pi, 10 pi. So the phase of the wave, phi 1, at the red X is going to be 10 pi. Now what's the phase of the wave that is coming from S2? We can do the same exercise. Say that every time we go from one peak to another peak, that's the difference in phase of 2 pi. So we just have to count the number of peaks, and we end up having, let's say, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12, 14, 14 pi, 16 pi. So phi 2 is going to be 16 pi. So now we can determine whether that point is, well, we already know that it's constructive because as you can see in the picture, the red X is at the superposition of the peak coming from S1 and the peak coming from S2. You can see that at this crossing right here, we have a peak superimposed superimposed to another peak. So we know that this should give us constructive interference. But we want to practice, we're practicing the concept of the difference in phase. So we calculate the two phases, one is 10 pi, the other one is 16 pi. So we know that the difference in phase is going to be 6 pi. 16 pi minus 10 pi is 6 pi. Since it's an even number of pi, this is constructive interference, as we just said, because the peaks are superimposed. Now another way to see whether there is constructive or destructive interference at a particular point in space is to look at the distance between the source and the point in space that you're talking about. So in this example, S1, the distance between S1 and the red X that we have here, which is right here, that distance is from S1 to the first peak, that's a distance of lambda. And then another distance of lambda from that peak to the next one, so we count here 5 lambda as the distance between S1 and the red X. For the distance with S2, you can count, and you'll see that it's 8 lambda, which gives us a difference in path length, the difference in the length of the path followed by the two waves. The difference in path length is 8 lambda minus 5 lambda, which gives us 3 lambda. Now a difference in phase of 3 lambda, it's equivalent, a difference in path length of 3 lambda is equivalent to a difference in phase of 2 pi over lambda times delta r. That's one of the equations that we discussed in previous videos. So if delta r is 3 lambda, that gives us a difference in phase of 2 pi times 3 lambda divided by lambda, which gives us, cancel the lambda, that gives us 6 pi. And the difference in phase is 6 pi, as we have already found before. So when you have a diagram like the one we just discussed, where we have two waves, two sources of waves, S1 and S2, there will be points in space where you have constructive interference, and there will be points in space where you have destructive interference. In this diagram that you're looking at right now, you see the red lines. Those represent the points along which we have constructive interference. Lines. Let's start, for example, let's take a look at one point that is on that red line that bisects S1 and S2. So that particular point that I chose here has a distance between S2 and that point of 3 lambda, and the distance between S1 and that point is also 3 lambda, which tells us that the difference in the path length difference is 0. Delta r, the path length difference is 0, which gives us a difference in phase of 0. The phase of S2 at that location will be 2, 4, 6 pi, and the phase of S1 when the wave arrives at that point that we chose is also 6 pi. The difference in phase 0. Any point along that red line, like this point, or this point, or this point, or any point in between, has a difference in path length of 0, and therefore a difference in phase of 0. So all of the points along that line that bisects the two sources have a difference in phase of 0, and therefore there is constructive interference everywhere along that line. Now if you pick a different point, like the one that I marked here with an X, you can see that, well, there is a peak superimposed with a peak, so that's going to be constructive interference also. That constructive interference at that point also occurs at this point and at any point in between them along this red line. Every point along this red line is going to have a difference in path length of lambda. You can count that the distance from one source is 2 lambda and the distance from the other source is 3 lambda. Therefore, the difference in path length is lambda, which gives us a difference in phase of 2 pi times lambda divided by lambda, which gives us 2 pi. difference in phase everywhere along that line is 2 pi. So notice that each one of these lines where there is constructive interference can be characterized by a delta r, which is a multiple of lambda, and by a difference in phase, which is a multiple of 2 pi. The next line that you see there, above that one, that line is, you can characterize it by a difference of path length of 2 lambda and a difference in phase of 4 pi. And finally, this other line over here will have a difference in path length of 3 lambda and a difference in phase of 6 pi. Now notice that along the line that connects the two sources, anywhere on that line there is a difference in path length. The difference in path length, delta r, is going to be a maximum. Notice how the difference in phase is going from delta r equals 0, right? This one, along the line that bisects the two sources, there's a delta r equals 0. As we move in this direction, the delta r is increasing. Now we have delta r equal lambda along this line. Then when we cross this line, the delta r is 2 lambda. And when we cross this line, the delta r is now 3 lambda. And so the delta r is growing as we move in this direction until we hit this maximum delta r line. Along this line, the difference in phase between the two sources is a maximum. How much is that difference in phase? Well, it's not very difficult to see that difference in phase, because we know that the difference in phase, we have an equation for that difference in phase. Difference in phase is 2 pi over lambda times delta r, and anywhere along that line, the difference in path length is going to be d, because this is the distance between the point where we're measuring an S2, that's what we call R2, and R1, the distance between the point in space and the source 1 is there, R1, and you can clearly see that R2 minus R1 is d. The difference in path length is d, the distance between the two sources. So the difference in phase at any point on that line is going to be 2 pi over lambda times d. That's the maximum difference in phase. So notice, as I said before, there are different lines, maxima, different lines along which you have constructive interference. The line that bisects the two sources has a difference in phase of 0. Then there's another line above that one that has a difference in phase of 2 pi, then 4 pi, etc. And the maximum difference in phase that we can find is along the line that connects the two sources. That difference in phase is 2 pi over lambda times d. So it depends on what's the distance between the two sources, distance d. So back to this example I showed you before. From the picture, we can tell that the distance between S1 and S2 is 3.5 lambda. 3.5 lambda. So what that tells you is that now we can say what's the difference in phase along the line that connects the two sources. What's delta phi maximum? In this case, since this is 3.5 lambda and delta phi is 2 pi over lambda times d, we get that delta phi should be 7 pi. It's 2 pi multiplied by 3.5. 2 pi times 3.5 is 7 pi. So notice that the line that bisects the sources has a difference in phase of 0, and the next line above that one is 2 pi, which is the maximum constructive interference, then 4 pi constructive interference, at 6 pi constructive interference, and then when we get to the line that connects the two sources, we have destructive interference. 7 pi is destructive interference. It's an odd multiple of pi, which gives you destructive interference. So if we were to move in a circle around S1 and S2, problem in the homework, we would count a number of maxima. Right? We would count a number of maxima. So the first maxima, if we move around and we count them, how many are we going to count? So that's the first maxima, it's start counting that one. So that's 1, that's 2, that's 3, that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14. 14 is the total. 3 here, 3, 6, 9, 12, and the 2 on the lambda bisects. 12 plus 2 is 14. So knowing the distance between the two sources allows us to find how many maxima you would encounter, how many would you encounter by moving around the two sources. Alright, I hope that helps you with the problem in the homework and to understand phase and difference in phase when there is interference between two sources in 2 or 3 dimensional space. Alright, see you next time.